Well, welcome back. I would like to apologize. We had some technical difficulties at the end of last week's video, so if you are watching online, you might notice that I seem to stop pretty abruptly. So what I'm going to do, we missed about 5 minutes. First 5 minutes of this class, this video, I've decided to redo the bit that got cut off. So the plan is then to do section 11.5, which is the missing material. The rest of the time will be chapter 12 of my book, which is sketching graphs. So the last little bit, what I was talking about last time, the deal is we have a critical point of a function. So that basically means that if x is a critical point, or let's call it c. So if c is a critical point, according to my definition, either the derivative at c is 0 or is undefined. This sort of critical point, it's interesting, but a lot of the time this is the real deal. This is the more common situation in a sense. I mean, we do know, for example, that a vertical asymptote will leave the derivative undefined because the function is undefined there. And we've also seen, for example, absolute value of x that has a sharp corner at the origin. So the origin is a critical point by this definition. But I would like to concentrate for the moment on classifying critical points of this form where the derivative is 0. And there are essentially 4 common possibilities, really only 3 if you look at it the right way. You could have a minimum, local minimum at c. You could have a local maximum at c. But you could also have a horizontal point of inflection. And there are 2 ways that that can look, or at least commonly. Right, so really there's 3 possibilities, 4 different pictures of it. The idea here is that the horizontal point of inflection, the tangent line actually passes through the curve here. So one half of the curve is below and the other half is above. Same thing in this picture. And actually, it's neither a maximum nor a minimum. It is a horizontal point of inflection, as I said. So how do you know which case you're in? Well, I'd like to just put the theory together. We've more or less got everything we need. There are based on what I've said last time, there are 2 different methods that you can use to classify these critical points. So the first method involves the first derivative. So the idea is this. Suppose we draw up a little table, and I'm going to expand on this table notion very, very shortly. But just for the moment, suppose I set up the table where I want to see what happens at x equals c. Well, there we know the derivative is 0. That means the tangent line is flat there. Now the question is, what if we go a little bit to the left of c, a little bit less than c? So I don't know how to squish it in. Maybe I can write a little less than c. And also check out what happens a little more than c. Okay, suppose that, say, the derivative happens to be negative here. So there's a minus sign, but positive here. So when we're a little bit to the left of c, the slope is negative. That means the function's going down. But when we're a little bit to the right of c, in this case, the function is going up. Because this must either be a local minimum, local maximum, or a horizontal point of inflection, Well, which one is it? It must be a minimum. So this would give a minimum at C. It doesn't mean that the curve looks like this. This is just to sort of give us an idea of how the tangents look, but you can clearly see it's a minimum. The curve is decreasing to the left and increasing to the right. The thing is, you've got to be quite close to C. You don't want to be so far away that you pick up, say, increasing here, increasing there. That's wrong. You've got to be close enough so that you avoid all the other critical points. Of course, if instead you had plus and minus, then you'd have a maximum. What if you had plus on both? Well, then you'd be in this case. Right? Here the derivative is positive everywhere except right there where it's 0, and then it's positive again. And of course in this picture it's negative all the time except for a brief flirtation with 0. So a table of signs for the first derivative, just concentrating on what happens near your critical point, will allow you to analyze which of these 4 cases you're in. Now, that's one method. Before we move on to the other method, let's see an example. Suppose we take y equals x log x. Or rather than y, maybe I'll call it f of x to be consistent with the previous notation. So f of x is x log x. We've already looked a little bit at this. Just to remind you, suppose we differentiate. Well, by the product rule, we get log x times the derivative of x plus x times the derivative of log x, which is 1 over x. And so this is just log x plus 1. Now, if we want to know where the critical points are, let's set this equal to 0. And this is true when log x equals negative 1 or x equals e to the minus 1, otherwise known as 1 over e. So there's a critical point at 1 over e. And just for yokes, we'll find out that f of 1 over e is equal to 1 over e, natural log of 1 over e. Of course, this is e to the negative 1, so the log of it is just negative 1. And we find that we have negative 1 over e. So somewhere on this graph, we know the curve goes through 1 over e, comma, minus 1 over e. Is that a minimum, maximum, or a point of inflection? Must be one of those because the derivative is 0 there. And that's the only place where the derivative is 0. So what is it? Well, let's set up a table of signs for the derivative. So here's x. Here is f of x. This time the critical point's at 1 over e, and there the derivative vanishes. This is the derivative here. Now, a number that is a little bit less than 1 over e, I don't know, let's take 1 over e squared. After all, e squared is bigger than e. 1 over e squared is less than 1 over e, rather. And I chose this because it's very easy to take the log of it. So, I don't know, the derivative is log x plus 1, log of e to the minus 2. So let's just set up a little table here. It's log of 1 over e squared plus 1. And if you compute this, this is minus 2, and this is 1. So you get negative 1. The only important thing about that is that it's negative. So the derivative, when you're a little bit to the left of 1 over e, is a negative number. A minus sign here. So the tangent is going downwards. How about to the right? Well, 1 is a number that's bigger than 1 over e. After all, think of e as about 2.7, between 2 and 3. So this is like a half or a third or somewhere in between. So 1 is certainly bigger. And if we calculate f prime of 1, it's just log 1 plus 1, which is 1, and that's positive. So the tangent is going up, the function is increasing there, and we have revealed that this is a local minimum. And we don't know anything else about the curve just from this particular piece of analysis, but we have analyzed this critical point at least. I'm going to come back to this very soon after I do the full method for graphing functions. But in the meantime, that is the first method. Now let me just show you how the second method works. This is another alternate method of classifying critical points. Instead of using the first derivative near the critical point, we'll use the second derivative at the critical point. So this is the second derivative method. So here's the deal. We've got these four situations. Maybe I'll just scroll back over here, if we wouldn't mind, and just take a look at these four situations here. This one, we've got a local minimum. The curve is concave up. So the second derivative is positive. In this case, we're concave down. So the second derivative is negative. So we'll sort of turn the tables around and write a little summary here. So if C is a critical point in such a way that the derivative is 0 there, what we can say is, first of all, if the second derivative at that point is positive, the curve is concave up nearby. So you should draw a little picture and remind yourself that we must have a minimum, local minimum, at C. And you don't have to remember this and this. What you have to remember is, oh, the second derivative is positive. Think of it as concave up. And you can see that it must be a minimum. Similarly, if the second derivative is negative, it must be concave down, and therefore local maximum at C. Now, what if the second derivative equals 0? You might think, and many students do think, that you therefore get a horizontal point of inflection. But it's not true. It's not true. You may get a horizontal point of inflection, but you may not. This test does not work. Use the first derivative instead. That's the first method. Method 1 that we just looked at. And to see why, I'll remind you of something we said last time. The classic example is f of x equals x to the 4th. The graph looks like this. It's sort of like a parabola, but it's really, really sort of boxy. It's very flat at the origin. It doesn't actually have asymptotes. It just goes up really, really quickly. But it does spread out. In any case, the point is that if you take the first derivative, you get 4x cubed. You take the second derivative, you get 12x squared. And this equals 0. Well, let's just say that x equals 0 is a critical point. So x equals 0. We have the first derivative, 4 times 0 cubed is 0. So we know the origin is a critical point. And the second derivative is also 0 if you plug it into that formula there. So you may be tempted to say, oh, critical point, second derivative 0, we must have a point of inflection. But as you can see from the picture, you don't. You have a minimum. So this is an example of where the second derivative test fails. Everything is great if your second derivative is not 0. It tells you exactly what's going on. But if the first derivative is 0 and the second derivative is 0, you cannot use the second derivative, at least not at 0, to deal with it. You may be able to do it by looking at what happens around 0. You'd find it was concave up in both cases when you were near 0, and that would lead you to the correct conclusion. But I think that if you do find this to be the case, that both the first and second derivatives are 0 at this point, or at any point, then you should use the first derivative method. Any questions on that? If you have one, I'm going to move now on to section, or chapter 12, and talk about sketching in general. So just shout it out. Okay, well, Chapter 12, as I said, is all about how to sketch curves. And the deal is that we've got a whole host of methods now, some not calculus, but also some calculus, especially this first and second derivative stuff. So all we have to do is put it all together. And we're sort of going to be detectives. We're going to gather little bits of evidence about certain parts of the function, and then we'll put it all together and draw the function, or at least our best guess of what it looks like. And sometimes the evidence will back up other pieces of evidence, and if it doesn't, as in contradicts itself, then you've probably made a mistake somewhere. So just, it's not quite CSI or anything like that, but that's the sort of mentality that I want to get into. We're detectives, and we're trying to detect what the function looks like. So before I get into a huge method of how to sketch functions, I do want to talk a little bit more about tables of signs. Now, I just drew up a table of signs for the first derivative, but actually there's three flavors they come in: the function itself, the first derivative, and the second derivative. And they each tell you something about the function. So let's just talk a little bit about tables of signs for a function itself. Forget calculus for the moment. The idea is going to be this. Suppose I have, for example, a function that I'd like to sketch. X minus 3, x minus 1 all squared over x cubed, x plus 2. Before we even do any calculus, one of the important things we're going to need to know is where does this function touch the axis and where does it blow up? So just inspecting it, we can see that x equals 0 and x equals minus 2 are bad. That's going to give us vertical asymptotes because the denominator is 0 but the numerator isn't. On the other hand, x equals 1 and x equals 3, the top vanishes, so there you're going to get x-intercepts. And on the graph, let's mark in the vertical asymptotes here, and then 1 and 3, we've got two x-intercepts. Okay, here is a really useful thing to know. Where is the function above the x-axis, and where is it below the x-axis? For example, if you know that it's always above the x-axis, say, in this region here, and we'll see whether it is soon, then it must look something like this. Maybe it has more wobbles in there, but it sure does not look like this, because it must be always above. There's no way it could get down here. Oh, well, wait a second, why doesn't it do this? Well, it might, but then the function wouldn't be continuous there. And really, what I want to do is I want to make a list of all the places where the function is either 0 or blows up or perhaps has a discontinuity. And in this case, it only does either, it only equals 0 or is not continuous at these 4 points. Minus 2, 0, 1, and 3. So there's no way it could do this. If it's positive for one point in here, it must be positive for every point. And I'm using the intermediate value theorem here to say that, you know, if it was positive there and negative there, because it's continuous in between these two lines, it must cross somewhere. And we know it doesn't, because we know that it only crosses here and here. So how do I exploit everything I've been saying? Well, I take what I said is a table of signs. Just out of habit, I'm going to include a third row. You've already seen how we used that the last time, but I don't actually need it for this particular thing. So I really only need 2 rows, but what the hey. What I'm going to do is put a whole lot of bars here, more if necessary. And I'm going to take these numbers in order, starting from left. The smallest is minus 2, and then 0, and then 1, and 3. And notice how I have left gaps around each one. What I'm going to do is pick a representative point in between each of these numbers, and also to the left of minus 2 and the right of 3. It doesn't matter what point you pick. It's just some sort of representative point. I choose the simplest thing I can, See, minus 3 is to the left of minus 2, minus 1 in between. How about 1/2 there between 0 and 1, 2 there, and say 4 to the right of 3. Now we know that the function is undefined here. I'm putting a star for undefined. And then we know it's 0 at 1 and 3. But the question is, what does it do in between? And in order to do this, you simply substitute this value of x into the function definition up there. But you don't actually care what the value is. You only really care whether it's positive or negative. And there's a real art to this. For example, if I plug in minus 3, I get a negative number. This thing's always positive because it's a square. I get a negative because it's cubed. And then minus 3 plus 2 is negative 1. So that's negative. So basically, I can write down, I don't know where to fit it. Maybe I'll just put it above. And I have a negative, positive, negative, and negative. So because there's sort of 3 negatives there, the total effect is negative. So I'm going to put in a minus sign. How about at negative 1? Well, that's still negative. That's always positive. That's still negative. But now that becomes positive. So we'll have just minus, minus, plus, plus. 2 minuses divided by each other will give you a positive. And in the same way, I can complete 1/2, 2, and 4. You don't need to substitute. You just need to look at whether each factor is positive or negative. So, you know, for 1/2, I get negative, positive, positive, so the thing will be negative. At 2, I get negative, positive, positive, positive. Again, it's negative there. At 4, however, everything is positive, and so there's my table of signs. So what do I do with it? Well, already I can confirm that whatever it looks like in between here, I do know it's positive, so it must look like that. Whereas to the left of negative 2, we saw that it's negative. So the asymptote goes down like that. How about between 0 and 1? Well, if you look here, between 0 and 1, 1/2 is the representative point. But it's true for any point between 0 and 1. The function is negative. So it must come down from here. To the right of 1, let's just take a look here. It's negative on both sides, actually, to the left of 1 and to the right of 1. So coming back over to the graph, we must just be touching at the intercept there. It doesn't go through. Whereas at 3, it does go from negative to positive. So actually, although we haven't finished, you see what I mean about being a detective? We've got a lot of the graph. We've got sort of a lot of the features. We still don't know what it does at infinity or minus infinity, and we don't know how many wiggles there are. There might be a whole lot of wobbling stuff there, or maybe there's only one. Actually, in order to find that out, you'd have to differentiate, and this example is a little too messy for us to differentiate by hand. So I'm not going to complete it per se, but nevertheless, I will come back to it and just finish off some of the features of the graph. So, okay, that's how you deal with the table of signs for the function itself. How about for the derivative? Well, we do the same thing for the derivative. It's just like the example that we did at the beginning. So, actually, before I talk about the derivative, maybe I'll just do one more example of the first one, because we're actually going to need this later. Suppose that, before I do the derivative, let's just look at this. We've seen this example before, actually, when we did inverse functions. We've looked at this function x squared times x minus 5 cubed. Okay, so what do we get? Well, there's no asymptotes, and the x-intercepts are at x equals 0 and x equals 5. So if I draw up a table of signs, looks like this. X, f of x, there's 0, there's 5, and we know that the function is 0 here and here. So what is it in between the cracks? Well, let's pick minus 1 there. I don't know, between 0 and 5, I'll pick 2, and to the right of 5, I'll pick 6. Once again, it doesn't matter. Now all I have to do is plug in these values. So when I plug in minus 1, that's always positive, but that's going to be negative. At 2, again, this is positive. That's once again negative. But at 6, everything is positive. So there's the table of signs. We immediately know that the curve is below the axis up until 5, except at the point 0 where it just touches the axis. Anyway, so that's a simple example. The reason I am looking at it is because now I want to show you the table of signs for the first derivative. So I'll use this example because it's not that hard to do. In fact, I did this a couple of weeks ago, or was it last week? I forget. The derivative turned out to be, it wasn't such a difficult calculation, but the derivative turned out to be, after factoring, 5x times x minus 5 squared times x minus 2. So there's the derivative. This now equals 0 when x happens to be equal to 0, 2, or 5. So there's 3 critical points. So this means now that my table for the first derivative, where I put f prime of x, I have to have a few more little sections. I have to do 0, 2, and 5. Now I'm going to have to go, say, minus 1, 1 in here. What do I want to pick, 3 or 4? Oh, what the hey, 3, and then 6 again to the right. Now we know the derivative is 0 here, here, and here, at 0, 2, and 5. And the graphical interpretation is that the curve is flat there. Now what about at negative 1? Well, we play the same game. We put it in. This time we get negative. That's always positive, and that's negative. So actually the slope is minus times minus is plus. And so the function is increasing there. How about at 1? Positive, positive, negative. So the function is decreasing. How about at 3? Positive, positive, positive. So the function is increasing. And at 6, positive, positive, positive. Again, increasing. So there's the complete table of signs. Now I'm not trying to say that the function looks like this sort of weird staircase. That's just a sort of guideline to see where it's increasing and decreasing. But the beauty of the table is that immediately you can tell what the critical points are in terms of max, min, or point of inflection, and you can say where the function is increasing and where it's decreasing. So let's summarize the conclusions of this table over here. We have a local maximum at x equals 0. Whereas at x equals 2, we have a local minimum. The curve's going down, that's the bottom, and then up. So local min at x equals 2. How about at x equals 5? Well, it's going up, and then it's 0, and then up again. So it's a horizontal point of inflection. Horiz point of inflection. I should write at in each case. At x equals 5. Another question, where is the curve increasing? Well, don't let the minus 1 fool you. That's just a representative point. In fact, it's increasing up to 0. So it's increasing when x is less than 0. Where else is it increasing? It's actually increasing everywhere to the right of 2, and even further, maybe not at 5, but 5 is just 1 point, and it still is increasing. So also, or when x is bigger than 2. Again, it's 2 that's important, not 3. 3 is just the sample point. 2 is where it stops being 0, and it's always positive after that, except for this moment at 5, which doesn't really count. On the other hand, between 0 and 2, that's the only place where the derivative is negative, so the function is decreasing when x is between 0 and 2. So the power of the table of signs, which is a major part of the curve sketching arsenal, is that you can tell where the function is increasing or decreasing, and also you can classify the critical points. How about the second derivative? Well, let's take the second derivative of this. I don't know if I ever did that before. Well, you know what? I'll just do it. I kind of want to save this area, so maybe we can do the computation on this board over here. So I'm going to rewrite the first derivative. In fact, I'm going to just display this for 1 second. I'm going to combine this factor and this factor for ease. So it'll look like 5x squared minus 10 outside of, it's 5x squared minus 10x, rather. Outside of x minus 5 all squared. Okay, let's differentiate this to find the second derivative. We'll use the product rule. So I turned the 3 factors that we had originally into 2 factors because it's easier to integrate by parts. So we're going to get the second factor, x minus 5 all squared, times the derivative of the first, which is 10x minus 10, plus the first factor, 5x squared minus 10x, times the derivative of the second, and by the chain rule, that's just 2x minus 5. I probably should have taken out a factor of 5 right at the beginning, but what the hey. Actually, there's a factor of 10 that pops out now. So also, if you look at it, there's a factor of x minus 5 in both of them. So let's pull out 10. Let's pull out x minus 5. The first factor, we're going to get an extra x minus 5, and we'll have an x minus 1. Whereas the second factor, that x minus 5, the 2 and the 5 I'm cunningly taking out as a 10, and you'll find you simply get x squared minus 2x. And then you just have to expand all this mess inside here. We're going to get 2x squared there. Well, let's just do it. X squared minus 6x plus 5 plus x squared minus 2x. So I believe that what you get is 10x minus 5 outside of 2x squared minus 8x plus 5. Now maybe I made a mistake. According to, nope, I don't know. I don't think I made a mistake. I don't think I did, although I might have. Well, indeed. The question is, how does that factor? Now, in order to really finish this off, we need to factor this quadratic. And I'm afraid we're going to have to use the quadratic formula. I've been stymied by the lack of light up there because now I've left myself no room to even use the quadratic formula. This becomes a bit of a mess, but let's see what we get. We're just trying to factor this quadratic, and we want the 2 roots of it, so I'm going to use the quadratic formula. X equals minus b, which is 8, plus or minus the square root. B squared minus 4ac is 64 minus 2 times 4 times 5. So it's 64 minus 40, which is 24. All divided by 2a, which is 4. Now 24 is 4 times 6, so this is 2 root 6. So if you simplify this, it's 2 plus or minus 1/2 root 6. Now does that agree with what I have computed earlier? Yes, miraculous but true. So I'm going to come over here and write this factored version. It's a bit of a mess. I get 10x minus 5 outside of 1 root is x minus 2 plus 1/2 root 6. And then another factor is x minus 2 minus 1/2 root 6. And that is the second derivative. I wish that it worked out better, but you can't have everything. If you can deal with these messy things, you should be able to deal with the nice things that often come up as well. In any case, this equals 0 when x equals 5, x equals 2 minus a half root 6, or x equals 2 plus a half root 6. And now we have to draw up a table of signs. It's going to be a little bit messy because of these messy numbers. So we have three numbers. The smallest one is clearly 2 minus a half root 6. How big is root 6? Well, it's less than root 9, which is 3. So this is less than 2 plus 3 halves. That's less than 5. And 5 is the next one. So actually 2 plus a half root 6 will be smaller than 5. Okay. Bear with me here. I know this is getting a little hairy here. We need a number less than 2 minus a half root 6. As we've discussed, root 6 is actually less than 3. So this quantity is positive, and so 0 is a good thing to the left. 2 is clearly in between these two, because this one you're subtracting, this one you're adding. And we decided that this was less than 2 plus 3 halves, which is actually less than 4. And then we'll pick 6 to the right of 5. So what have we found? We found that the second derivative is 0 at these 3 points, and we're just going to fill in the cracks, and we want to look at this monstrosity here with these 3 factors, which kind of spilled onto 2 lines, and we want to see what happens when we plug in 0. Well, when x equals 0, that factor is minus 5, that's minus this mess, and this is minus this mess. All of these messes are positive, so you actually get negative, negative, negative because of the minus signs. So the second derivative is negative. However, at 2, this is negative, but that now becomes positive. At 4, that's negative, but these two are positive. And so you will get negative, and then finally at 6, you get positive. If you don't like to substitute these numbers into this mess, you can substitute them actually into this expression over here, which is the derivative before I factored that messy quadratic, and then you can just plug them in and see whether you get a positive or a negative number. Anyway, I'd like to come back over here and interpret what it means for the second derivative to be negative. This means you are concave down. At 0, there's not really much you can say, but then you're concave up, because it's positive, then concave down, and then concave up again. So actually, you do have points of inflection, not horizontal necessarily, but you have points of inflection here, here, and here, because the second derivative changed sign in each case, going from negative to positive or from positive to negative. So this table tells us where we have points of inflection and where the concavity is up or down. So let's summarize. We have inflection points, which I will write infleputs, but you understand, hopefully, that I mean inflection points. And we see that we have one at 2 minus a half root 6, 2 plus a half root 6, and 5. So those are the 3 inflection points. Where is the curve concave up? The answer is not necessarily at 2, but rather between 2 minus a half root 6 and 2 plus a half root 6. Again, 2 is just a representative point. And it's also concave up to the right of 5, 6 being the representative point. So I'm going to write conc up to mean concave up, and I'm going to use the interval notation so I can squish it in this little space. It's concave up on, well, 2 minus a half root 6 to plus a half root 6. Also to the right of 5. And it's concave down. This is really squishing it here. It's concave down everywhere else. Minus infinity up to 2. Is this even visible on the camera? Yeah? Okay. I'm really struggling here. So it's concave down from minus infinity up to 2 minus a half root 6, as well as between 2 plus a half root 6 and 5. I don't even know if I can write that. What am I going to do? You know, I'm just going to rewrite this up here. Concave up on 2 minus a half root 6 to 2 plus a half root 6, as well as to the right of 5. And it's concave down on minus infinity up to 2 minus a half root 6 and 2 plus a half root 6 up to 5. I need a high-res blackboard. Okay. Now I'm going to save all this because I'm going to use it all to sketch this curve. But not yet. I want to just do one more example since that one was so contorted. I'd like to show you just one more example of the second derivative for a table of signs for the second derivative. And then I intend to do the big grand method of how to sketch any curve. So before I do the method, as I said, let's just consider g of x is x to the 9th minus 9x to the 8th. Now I don't propose to sketch this curve. I kind of want to leave it up to you, but I do want to show you how the second derivative table of signs works. If I take one derivative, I find I get 9x to the 8th minus 72x to the 7th. If I take another one, actually, let's take out a factor of 9 first. You will find you get 9 outside of 8x to the 7th minus 56x to the 6th. You can take out a further factor of 8 and get 72 outside of x to the 7th minus, is this what I wanted? I guess it is. I get x to the 7th minus 7x to the 6th. Let's just factor this down a little bit more into 72x to the 6th outside of x minus 7. So this clearly equals 0 if x equals 0 or x equals 7. Those are the 2 points. So let's set up a table of signs for that second derivative. And I'm going to have x, I've called it g, so I'll write g double prime of x. Zero and 7 are the important points. Second derivative 0 there and there. So let's just pick some representative points, say minus 1, 3, and 8. And if I plug in minus 1 into here, I'm going to get x to the 6th is always positive, so I'm just going to get negative. Similarly, at 3 I'm going to get negative, but at 8 I'll have positive. So if I actually draw this, I'm concave down there, I'm still concave down here, and then I'm concave up at 8. Now the reason I produced this example is to say that you are wrong if you think that there is a point of inflection at 0. There is not a point of inflection at 0. If there was, then the concavity would either have to go from positive to negative, like at 7, or from negative to positive. But it doesn't. It stays negative. So actually, this point is probably going to be a maximum. It's going to be something like this. Whereas here, we will get a horizontal point of inflection. So this is a sort of fake-out situation. It's not actually a point of inflection, despite the fact that the second derivative vanishes. Only this is the point of inflection. This is not. Okay, so that's a cautionary example. Okay, great. I've sort of burbled on about tables of signs and given you examples. What's the whole point? To help you sketch. But there's more that you need in order to set it all up. What I want to do is present the method. A lot of the method is geared towards finding these tables of signs, because once you know them, you almost know everything. So let's state the whole method. How many steps have we got? 11 different steps for sketching a function. What I'm going to do is try to fit it on boards and save that last board, because I'm going to eventually come back and sketch that function. But let's see how we go. So here's the method. The first thing I think you should check is the symmetry. Is the function even, odd, or neither? Okay. Let me remind you how to check that. What you do is you plug in minus x instead of x. So you're trying to sketch y equals f of x. You take your function and you replace x by negative x. And you simplify it, blah, 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 and see if you can pull out minuses out the front. Maybe you can get it to f of x. Maybe. If you're just lucky, all the minuses will go away, and it will look like your original function. In that case, the function is even. And remember, the beauty of that is, if you know it's even, you only have to sketch what happens to the right of 0. Because then, to the left of 0, it's just a mirror image. You just copy everything and flip it over. But maybe, instead of getting f of x, you get your original f of x, but with just one minus sign out the front. And if that happens, then it's odd. And then, again, if you've sketched it to the right, you can fill in the rest. This time you pretend that the whole thing is like a solid piece of metal, like a paper clip bent out. And imagine that you pivot it around this point. So you will get something like this. So I'm just going to pivot it, turn it 180 degrees there, and that fills in the left. So you actually only have to do half the work. You don't have to bother analyzing all 4 critical points, for example. You know these 2, and that automatically gives you the other 2. That's kind of nice. But if it's neither, which happens most of the time, I'm afraid, then there's no symmetry and there's no extra information. So you've sort of wasted a few seconds. You know, it doesn't take very long most of the time to see whether a function is even or odd, and it's worth taking the time just in case it is, because then you'll save a lot more time. So it's a sort of gamble, but I think it's recommended. Right. So the second possibility, or the second thing to check, is find the y-intercept if it has one. It never has more than one y-intercept, at least not if it's a function. Functions have to obey the vertical line test. So to find the y-intercept, set x equals 0. And then that tells you the value of y if it exists. Of course, it may not exist. The function may blow up there, in which case there would be no y-intercept. Okay, find the x-intercepts. There might be more than one, so I'll write x-ints. Just set y equals 0 and try to solve for x. That is not always easy. If it's a quadratic, you may have to use the quadratic formula. If a factor is a quadratic, ditto. If it's, say, a cubic or higher, you may have to guess a root and try a long division, perhaps. It could be exponentials, logs involved. You know, you just have to try to solve the equation to find the x-intercepts. Not always possible. The next thing you should try to identify is the domain of the function. Arguably, this should have been done right at the beginning. I don't know, some of the order of this early steps, it's independent, it's up to you. But let's just talk about, let's just put it here, what the hey. So how do you find the domain? Well, basically, unless you're told otherwise in some question that you're dealing with, the domain is as much as possible. It's as many points as you possibly can. So basically, I take the attitude of assuming that it's everything unless there's a screw-up. What is a screw-up? That's not a very technical term. I would try to avoid using the word screw-up when you write your midterms or your finals. But nevertheless, I want to have this idea that you have a screw-up when the denominator is 0. That's normally a death knell for the function to be defined there. You can't really have 0 on the bottom, so that is a problem. Also, you cannot take the square root of a negative number. That's bad. That will certainly cause a point not to be in the domain. The other common possibility is that you can't take the logarithm of a negative number or even the log of 0. Natural log of 0. These are bad. That's going to cause points not to be in the domain. So those are the common possibilities amongst the functions that we're looking at. There are certain values. I mean, tan of pi over 2 is undefined, but that's actually because the denominator is cosine. Tan is sine over cosine. So, you know, I guess there are some other possibilities. Inverse sine, for example, the domain of that is -1 to 1 inclusive, so you can't take inverse sine of 2. But these are the three most common screw-ups. Otherwise, a point is in the domain. So that's all I have to say about that. Now, if the denominator is 0, you probably have a vertical asymptote. So step 5 is to try to identify the vertical asymptotes. These occur more or less when the denominator equals 0. They also occur, for example, log has a vertical asymptote at 0. That has a vertical asymptote. We know the graph of log x. I've sketched it many, many times. It has a vertical asymptote, even though it doesn't have a denominator. And so anything with a log could conceivably give you a vertical asymptote. There is one cautionary point. If the denominator is 0, you may, in fact, have a removable discontinuity, not a vertical asymptote. And an example is provided by something we looked at quite a while ago. There's many examples of it, but if you just take, say, I don't know, y equals x squared minus 3x plus 2 over x minus 2. And if you were to put in x equals 2, you'll see, oh, the denominator is 0, so we must have a vertical asymptote. No, the numerator is also 0. You get 4 plus 2 is 6 minus 6. So you get 0 over 0, which is an indeterminate form. Remember, that means that we can't just tell by looking at it what it is. It could actually be a vertical asymptote, or it could be, as it is in this case, a removable discontinuity. In fact, this is equal to, if you factor the top, you'll see that x minus 1 is the other factor. So this actually equals x minus 1 if x is not equal to 2 and is undefined when x equals 2. And we looked at this exact function way back on the second video, second week, when we looked at limits. Doesn't seem like all that long ago. In any case, it looks like this. So it doesn't have a vertical asymptote. Instead, it has removable discontinuity. So I guess this is a... So vertical asymptote, the denominator equals 0, and the numerator is not 0. Or maybe if the numerator is 0, but then you have to check it very, very carefully. All right, we still have a little more work to do on the method. Are there any questions? I'll leave this up. I'm going to erase the top board, so shout out anything if you have one. All right. So continuing on with the method, we're almost halfway there. Step 6 is to draw up a table of signs for the function. For f of x. And I already talked quite a lot about how to make a table of signs, so I'm not going to do that again. The thing is, though, you need to know where the function is discontinuous and where its x-intercepts are, and that's provided by steps 3 and 5. 3 was the x-intercepts, and 4 is the domain. You can see where it's not defined, and 5 the vertical asymptotes, or even the removable discontinuities. These sort of tell you what values to drop into your table of signs. So that's where I think you should do that. Now, we've also got to look at step 7, horizontal asymptotes. How do you find those? Well, what you do is you take the limit as x goes to infinity of f of x. And also x goes to minus infinity. Find those two limits. If this happens to equal L, say, then you have a right-hand horizontal asymptote at L. And if this happens to equal M, you have a left-hand horizontal asymptote at M. Of course, if the limits don't exist, you don't have horizontal asymptotes. Or if the limits are infinite. So, in that case, there is some potential for diagonal asymptotes, and I don't want to talk about that right now, but I'll look at an example later on where we can still, even though we don't have horizontal asymptotes, we can still sort of understand something about how the function behaves at infinity. So let me just leave it at that for the moment and then come back to that point when we look at some examples. Okay, I want to say that although we've used a few limits, we haven't used any calculus proper yet. We haven't used any calculus. So the last 4 steps are designed, are the calculus piece. So this is really the extra piece that we have. So step 8 is find the first derivative. Find where it's 0. The first derivative is 0 or undefined. And draw a table of signs. For f prime of x. And again, I've told you all about how to draw the table of signs. So I'm not going to belabor that at the moment, although we will look at a whole lot of examples. Draw a table of signs. That, as we've seen, gives you a heck of a lot of information. However, there's one extra step. Use the table of signs, as we've done, to classify maxima and minima. And horizontal inflection points. Let's say horiz inflection points. What you really need to do is plug in those values, the max or the min, the x values, into the original function, not the derivative, into the original function. Plug in each of these x coordinates into the original equation y equals f of x in order to get the y coordinates, and then mark these things on the graph. In fact, I should have said that you should try to mark as many of these things on the graph as you go along. So you can mark in the asymptotes, vertical, horizontal, mark in the intercepts as you find them. So that's sort of useful. In this case, you cannot draw the maximum or the minimum unless you know how high it is. And the way to find that is to plug in the value of x that you're interested in. In this case, every max or every minimum and every horizontal inflection point, individually you plug them in. And so you know how high these points are. So that's sort of steps 8 and 9 that are going together there. Steps 10 and 11 are similarly paired, but they involve the second derivative. So find the second derivative. Find where it's 0 or undefined. And table of signs for the second derivative. And then step 11 is the companion step. Use the table to find the inflection points. Again, most of the time, if the second derivative is 0, you do have an inflection point, but as we saw before, you may not. So you have to sort of use the table, and then again, plug each one into y equals f of x to find the height, or the y-coordinate, of the inflection point. Of inflection points. And finally, mark on the graph. Whew, that's a long method. That's a long method, and it does take a while. Each example takes a while. But that's what you have to do if you want to do it properly. And once you get all this information together, you will see that everything just fits together, and you can pretty much just connect the dots. The whole thing becomes a connect the dots in little snippets of lines. All right, so it's about time we actually sketch some graphs. So are there any questions? Again, just shout it out if you have one. Well, no questions. All right. In that case, let's look at some examples. So actually, the first example I'm going to label as example 0, unfortunately. I don't know what to call it. It's an example that I'm going to sort of, I'm going to wimp out really, and I'm not going to use calculus. Actually, it's just the one that we looked at before when we drew up the table of signs. Y equals f of x is equal to x minus 3, x minus 1 all squared over x cubed, x plus 2. That was the first example that I looked at for table of signs, but I just want to sort of start you off. Again, I'm not going to do the last 4 steps here, which, as I say, I'm wimping out, but let's see how the first few steps look. First one was to check the symmetry. So if I plug in minus x, I get minus x minus 3, minus x minus 1 all squared, minus x cubed, minus x plus 2. It looks like a bit of a mess. Let's pull out some minus signs and see what we get. We get minus x plus 3, x plus 1 all squared. Actually, the minus doesn't need to come out of there because of the square. Here I'm going to have minus x cubed and another x minus 2. Another minus turns that into a plus. You know, I'm sort of belaboring this a little bit, but it doesn't actually look exactly like the original here. So it is pretty lousy. It's neither odd nor even. Nothing I can do about it, I'm afraid. Okay, so that's step 1, no symmetry. Dull. What are we going to do? How about the y-intercept? Well, x equals 0. You have y is f of 0 equals, well, unfortunately, you have a 0 on the denominator, so it's undefined. No y-intercept. Step 3, x-intercepts, you put y equals 0, and then you can see x equals 3 or 1, as we said before. If a fraction is 0, its numerator has to be 0, and the only way x minus 3 times x minus 1 all squared can be 0 is if either x equals 3 or x equals 1. So there's two x-intercepts, as we noticed before. How about the domain? Well, again, it's only bad when the denominator vanishes. So it's everything except x is 0 or x equals negative 2. Maybe I'll come over here and do step 5. So for step 5, I'd like to look at the vertical asymptotes. The only possible candidates are x equals 0 and 2, and the only thing that could screw that up is if the numerator was 0 as well, but it's not. The denominator is 0 and the numerator is not. So I have vertical asymptotes at 0 and minus 2, not 2. Sorry about that. It is 0 and negative 2. Okay, well, step 6 calls for the sign of the function, but you know what? I've already done it. Just to remind you, here it is in context. The idea was that I put in the vertical asymptotes and the x-intercepts in ascending order and then filled in the cracks with prospective values or sample values. Here f was undefined. There it was 0. So we have vertical asymptotes there and x-intercepts there. And then we found that it was negative, positive. I'm going to cheat and look at what it was because I can't actually remember. Negative, negative, and positive. Okay, so again, all I had to do there was to substitute these values into the original expression for f. This is not 6x, this is step 6. All right, the last step before calculus, step 7, is to try to see what happens as x goes to infinity. So let's take the limit as x goes to infinity of the function. X minus 3, x minus 1 all squared over x cubed times x plus 2. Well, the simple thing to do is to notice that the top has degree 3 and the bottom has degree 4. But you actually don't have to do that. You can do it using my polynomial limit method, which is to take this x minus 3 factor, divide by x, and then remultiply by x. And then, because x is the leading term, do the same for x minus 1 all squared, except now you have to correct by multiplying by x squared. And then on the bottom, x cubed doesn't do any harm, and x plus 2 I can write as x plus 2 over x times x. And the point of doing these manipulations is that this x squared, this x, and this x cubed give me one factor of x on the bottom. All the rest of it is 1 plus or minus silly stuff. So you get 1 minus 3 over x. Well, that goes to 1. 1 minus 1 over x goes to 1. 1 squared is 1. 1 plus 2 over x goes to 1. Everything here goes to 1. This is the only thing left. And because of this x, this limit equals 0. You end up with 1, 1, 1, and a huge number on the bottom. So the limit is 0. And the same argument works as x goes to minus infinity. So there is a, and you should try that, there is a two-sided horizontal asymptote at y equals 0. See why we do all these limits, polar over polar? I mean, it directly relates to how to sketch the curve. Anyway, I've been bad more or less because I was limited by having blackboards to write on, but I should have collected the information Actually, I already did it earlier, but let's put it all on the graph. Step 1 said neither. Step 2, no y-intercept. X-intercepts at 1 and 3. Step 4, the domain, we're okay except at -2 or 0. And from step 5, they're both y-intercepts. The table of signs told us that it was positive here, and that it was negative down there. And we also knew that we were negative here and here, but positive there and negative here. So that's what we already had. Actually, the new piece of information that we have is that we have a two-sided horizontal asymptote at 0. How did I know that it was above there and not below or oscillating? Because the function is always positive to the right of 3. That's from the table of signs. And similarly, since it's negative down here, it doesn't cross the axis. It must be negative on that horizontal asymptote as well. So again, without using calculus, I cannot diagnose how many wobbles there are, but it seems reasonable, based on what we know, to just connect this and this, to connect this somewhere. Again, I don't know where this is, whether it's in the middle or over the left, or if there's more than one, or how high it is, but I can still get a general picture that the graph must look something like this. And actually, if you graph it on a graphing calculator or on a computer, then you should find that it looks something like this. So there's our first example. As I said, if I wanted to find out where these points are, I would have to use calculus, but I'm too scared to differentiate that mess. What can you do? All right. The next thing I'd like to sketch, so that's the first example. I like to do a sort of comic relief one. I say that because it's actually quite easier than the other examples I'll look at. And it's that function that I started off with. We looked at it right at the beginning of this particular class when I was redoing that part that got missed at the end of the last class. And that is the function f of x equals x log x. So again, we've already done some of the work. So this is the first proper example. If I have time, I'll do 4 full examples of the 11-step method. Yes, 4 is my plan. So x log x is the first one. Let's just whip through the steps here. Step 1, if I take f of minus x, well, that's a problem. I'll just have to write because if x is, say, 2, I can't take log of minus 2. So clearly it's not symmetric. It's not even defined to the left. This is where knowing the domain first might have helped, but never mind. We'll get there in the end. F of 0, so to get the y-intercepts, f of 0, 0 log 0, no good. Can't take log of 0, no y-intercept. Okay, how about the x-intercepts? Well, f of x equals 0, put y equals 0. Y is the same as f of x. So you get x log x equals 0. When does that happen? When either x equals 0 or log x equals 0. Unfortunately, x equals 0 is no good because if you plug in 0, as we saw, log of 0 is undefined. So that's not allowed. But log x equals 0 is fine, and that will happen when x is e to the 0, which is 1. Log 1 is 0. So we have an x-intercept at x equals 1. And I'm going to start drawing the graph up here. So we already know that, well, let's put it here. There's an intercept at x equals 1, so the curve goes through that point. Okay, step 4, the domain. Well, log x doesn't exist when x is 0 or negative, so this thing only has domain x greater than 0. And now you can clearly see that there can't be any symmetry. If there was, then the other half of the graph would either be the mirror image or the twisted image, but there is no other half of the graph. So that's the domain. So how about step 5? Well, step 5 is to look at vertical asymptotes. There's no denominator, so that doesn't happen. There might be one because of the log. Maybe x equals 0 because of log. I don't know. That's a tricky point. We're going to have to come back to that. Actually, if you really want to know what happens, take the limit as x goes to 0 from above of x log x. Why from above? Because there is no from below as far as log's concerned. From above, this is actually a limit that we've seen when we looked at exponentials. It's in chapter 9. It was sort of complicated. When we do L'Hopital's rule in a few weeks' time, we will see that this limit is 0 by using a different method. But actually, we already have seen, I think, that this is equal to 0. So there is no vertical asymptote. Instead, we will find that there's a removable discontinuity at the origin, because as x goes to 0, the height of this thing goes to 0. All right. Step 6. What is step 6? I'm losing myself here. The table of signs for the function. Well, let's just draw it up. So we have x and f of x. And it's a very simple table. It's a very simple table. We know that the function is 0 when x equals 1. So when x is less than 1, say 1 over e or e, notice how I could have picked a half. Couldn't pick 0 because f of 0 is undefined, but I could have picked a half. But I picked 1 over e because I kind of know that 1 over e log 1 over e is easy to deal with. It's just minus 1 over e. I can tell it's negative. Whereas at e, I get e log e, which is just e, and so it's positive. So actually, I can depict this on the graph over here by showing that at 1, to the left of 1 it's negative, and to the right of 1 it's positive. Now, I want to leave all this garbage underneath here up for the next example. So I'm going to pause mid-problem, as it were. I do want to work the other steps. So I need some room. All right, step 7 is to check the horizontal asymptotes. So step 7, let's take the limit as x goes to infinity of x log x. Well, this is not so hard. As x goes to infinity, x becomes huge. Log x also goes to infinity. So this is a product of large things. So it goes to infinity. As for the left-hand limit and minus infinity, that clearly doesn't exist because you can't even define log x to the left. So on this picture, coming back to the picture, we know it goes up to infinity. So we know a little bit more about the graph. Now let's find out even more by using calculus. As we saw, we take the derivative, x log x. We found that it was equal to log x plus 1 at the beginning of the class. And so we now find that this equals 0, again, when x equals 1 over e. And we had already drawn up the table for the... So this is, well, maybe I'll do it down here. Step 9 was the table. Actually, no, I put that in step 8. I stand corrected. The table belongs in step 8, so let's do it there. You can do it wherever you want. These are just my steps, by the way. But anyway, when x equals 1 over e, we found the derivative was 0. And as you might recall from the very beginning of this session today, we found that the derivative is negative here, positive there. So look back at the beginning, and you'll see that we indeed have a minimum at 1 over e. So x equals 1 over e is a minimum, local minimum. Now, step 9 says we have to analyze this, or at least find the y-coordinates. F of 1 over e is equal to, we go back into the original 1 over e log 1 over e, not the derivative, the function itself. This is negative 1, so it's minus 1 over e. And so we now can come back over to the graph, and we can mark in the point 1 over e, comma, minus 1 over e, and we know that there's a local minimum there. And just to emphasize it, I'll draw a little tangent, and that's got to lie below the curve because it's a minimum. Well, we're very close to being done. We just come over here and finish the second derivative. That's step 10. Just remind you that the first derivative we found was log x plus 1, so the second derivative is 1 over x. And there's not much of a table of signs that you need because we know x has to be positive, so actually this is always positive. The table of signs is sort of useless. Always positive over in the domain x greater than 0. So it's always concave up, i.e. f always concave up. And in particular, there's no points of inflection, because the second derivative is never 0. And also, this corroborates the fact that it's concave up, that x equals 1 over e is a minimum, because the second derivative is positive there. I should have checked that earlier when I was talking about the second derivative as a test. But here it is. In this example, even if you didn't believe the sign of the first derivative, you will see that the second derivative is positive. So actually, I kind of made a mess. You can tidy it all up. But the curve must look something like this. It has a minimum at 1 over e, comma, minus 1 over e. It's quite clear, by the way, that this does not go down to minus infinity. Even if you didn't know this limit over here, that the limit is 0, the limit could not be negative infinity. It couldn't be anything positive as well because this curve is negative. Maybe it could have been minus 1/20th or something like that. Anywhere between minus 1 over e and 0 would have been fair game. But as it turns out, the limit is 0. And it crosses at 1 and it sails off to infinity. So not so bad. Okay, so as I say, that wasn't such a tough example, but I do want to look at 3 more. Hopefully I'll have time. Step 11, by the way, here there was none, because there's no points of inflection, not even any potential candidates. All right, so moving right along, let's look at example 2. Now this is the magic one that I already did before, so this is y equals f of x equals x squared outside of x minus 5 all cubed. Okay, so you'll be happy to know that we don't have to worry about tables of signs because they're all hiding under this left-hand blackboard, which I will expose imminently. But let's just run through the steps again. Symmetry, put minus x, so we get f of minus x is minus x all squared minus x minus 5 all cubed. If you work it out, you get the minus goes away here, but it can pull out here because of the cube. So you get minus x squared x plus 5 cubed. It's not the same as the original function, but it's not even the negative of the original function, because here you have an x minus 5, and there you have an x plus 5. So it's neither. Sorry, can't do anything about it. Now, step 2, y-intercept, f of 0 is 0. Just plug in 0, you get 0. So there's a y-intercept at x equals 0. The x-intercepts, again, put y equals 0, and you see that x has to be equal to 0 or 5. This is nothing new here. Step 4, well, that is to find the domain, and it's clearly everything. There's no number that you can plug in and cause a screw-up. So it's everything, and therefore there's no vertical asymptotes. As for step 6, we've already done. I'll expose that in a few seconds. Step 7, limit as x goes to infinity of x squared, x minus 5 all cubed. Well, that's infinity. Why? Well, when x is huge, x squared is huge, x minus 5 all cubed is huge, product is huge. How about the negative infinity version? Well, now we have to be a little careful. This is huge positive, but because this is a negative number cubed, it's going to be a huge negative number. So this is minus infinity. Okay? Now, I'm going to erase this. And then I am going to expose the bottom board so we can see what's left. We've almost done everything of the rest of it because we took all that time to do the table of signs before for the derivative and the second derivative. So let's just expose this again. This is step 6, this is step 8, and this is step 10. So the table of signs for the function is over here. The table of signs for the first derivative is here. And for the second derivative is there. So you can look back at your notes. This is all in the book in section 12.1.2, I believe. You can find, and actually 12.1.3, you can find all of these tables there. So, in any case, the one thing we have left to do, having done all this, is we didn't find any of the y coordinates. In particular, we're interested in these critical points at 0, 2, and 5. We need to know what the y coordinates are. And similarly, for these points of inflection at 2 minus a half root 6, 2 plus a half root 6, and 5. So I'm going to need to come back over here and just summarize the points from these tables of signs here before actually drawing the graph. Okay, so step 8 and 9, see before, we found a local max at x equals 0. And at that point, we need to just substitute into this equation here, which is the equation for y, and we found f of 0 is 0. We also have a local min at x equals 2. So we need to find f of 2. Well, what is that? That's 2 squared times 2 minus 5 all cubed. 3 cubed, this is minus 3 cubed actually, it's negative 27 times 4 works out to be negative 108. Negative 27 times 4. So there's a local min, I should have said a local max at 0, 0. The local min is at 2, negative 108. And the horizontal point of inflection at x equals 5, and f of 5 is 0, as you can see from plugging it in. So the horizontal point of inflection is at 5, 0. Now I'm going to have to repeat this for the second derivative, but for the moment I actually want to set up the graph of this function. Now I think this is within the angle of the video if I draw it here. So let's just set the whole thing up. What do we know? Well, looking back, step 1, no symmetry. Step 2, there's a y-intercept at 0. Step 3, x-intercepts at 0 and 5. Step 4, 5, nothing to say. Step 6, we know that the function from the table of signs, it's all the way back over there, but I'll just remind you that it's negative here, and that it's positive to the right of 5. So it must go like this through the 0 at 5, but at the origin it must do something like this, because it doesn't cross the axis. Step 7 said the limit at infinity is infinity, and the limit at, as x goes to minus infinity is minus infinity, so it looks something like that. Now, step 8 said we have a local max at x equals 0. Hey, we already knew that just from the table of signs of the function, But this is what I mean about consistency. If we'd found that this was a local min, we must have made a mistake somewhere. You have my permission to go, what the, or whatever. You have to decide which one you made a mistake in. Was it the table of signs for f or the table of signs for f prime? You have to be consistent. What else do we know? We knew that there is a local minimum at x equals 2, and that the x-coordinate there is minus 108. So this is not to scale on the same scale on both axes, obviously, because that's 108 and that's only 2. But we also know that there's a horizontal inflection point at x equals 5. So that drawing, although it captures the fact that it goes from negative to positive, is not adequate for how it goes from negative to positive. Because it's a horizontal point of inflection, it must flatten off and actually go through like that in such a way that the x-axis is the tangent at x equals 5. Nice. So there's the minimum. There's still a little bit more work to do. We have to come back over here and finish steps 10 and 11. Now, we know that we have inflection points. Well, one inflection point is x equals 2 minus a half root 6. So the question is, what is f of 2 minus a half root 6? And now I am going to perform another bit of a cop-out, I'm afraid. See, I want to take the original equation and put x equals 2 minus a half root 6. Unfortunately, to expand it would be a real pain. I could use a calculator to get an approximation. I could use a computer or just be very patient and expand the whole thing out. It's a real mess. It's a real mess. So I am just going to call it alpha. I don't know what it is. It's some number. I could compute it if I really wanted to, but it's messy. And I'm similarly going to cop out for the other one and just call the height beta. Now, it's not that these are mysteries. They're absolutely known. We know exactly what they are. It's just there's no nice way to write them. You could write it out as 2 minus a half root 6 all squared times negative 3 minus a half root 6 all cubed. I prefer to just call that alpha. On the other hand, 5 is the last inflection point, and we know that's equal to 0. So how do I put these facts on the graph? Well, somewhere around here is 2 minus a half root 6. Somewhere around here, actually on the other side of 2, but the same distance away, is 2 plus a half root 6. And then whatever these heights are, alpha and beta, I am filling in the curve here. And I'm going to have to tidy it up. So the point is that it's concave down here, and then at this point, so this is why you should always do these sketches in pencil to start off with. At some point, it switches from concave up to concave, from concave down to concave up. And to symbolize this, I've sort of drawn the tangent at that point, which is through the curve. It's a point of inflection. Similarly, over here, the tangent sort of goes through. It's kind of hard to draw, but the height there is beta. Actually, I think I plugged them into a calculator and found that they are very close, these numbers, alpha and beta. But in any case, the other point of inflection we already knew about, because it's a horizontal point of inflection. And then all that's left is to fill in the rest of the graph. That goes up there, that goes down there, and that's pretty much what the graph looks like. So notice that we have identified the maximum, the minimum, the horizontal point of inflection, the other 2 points of inflection as well, although I've left the y coordinates there in some reduced form. A lot of work. Don't forget, that was quicker because we did a lot of the work beforehand. You had to take those derivatives. So this is a quite involved and nasty example. If you can do this one, you can probably do anything. But I still have another 2 examples that I want to do, and I still have about half an hour to do them. So now I can finally dispense with this information. We've squeezed every little bit we could. Does anyone have any questions about this before I do the next example? So, you know the drill. I know you can't ask questions if you're watching it online. Haven't worked out that technology yet. Send instant messages into the past or something like that. That'd be kind of clever. All right. Time for another example. Remember, practice these things. They take a while. So you should try to do at least 5 or 6. Suppose we want to sketch y equals f of x, which is the function x e to the minus 3x squared over 2. So that's what we're going to be working with for a while. All right, let's follow the program. 1, symmetry. What is f of minus x? Well, it's minus x e to the minus 3 minus x all squared over 2. And so, actually, the minus x all squared is just x squared. So you get negative x e to the minus 3x squared over 2. Actually, this is the same as the original function, except with a minus sign outside. And that is good. This is minus f of x, and so the function is odd. This is great. We only have half the work to do from this point onwards. Okay, 2, y-intercept, f of 0. Just plug in 0 and you get 0. No problems. How about step 3, the x-intercepts? Set f of x equals 0, or y equals 0, and we'll have x e to the minus 3x squared over 2 equals 0. Now, here's something about exponentials. They're always positive. Exponentials are always positive. E to the anything is a positive number. So don't get bogged down by this being negative. It doesn't matter what it is. You cannot have that factor being 0 or even negative. So the only solution to this is x equals 0. There's no way that quantity can be 0. Only in the limit, maybe, as x goes to infinity, but that doesn't count. So x equals 0 is the only x-intercept. So if we actually start building up the graph over here, actually, maybe I won't do it over there. It's nice to have some room. I think I'm going to just come over to this little board here and set it up there. So we're going to be moving back and forth and putting the information on this graph. So far, we know that it's odd, and we know that the only x or y intercept is at 0. Okay, that's not very much to go on yet. Step 4, the domain, again, there's no problem. Even if you write f of x as x over e to the 3x squared over 2, it doesn't matter. The denominator is never 0. Again, exponentials are always positive. There's no problem spots, so it's all of r, and by the same rationale, no vertical asymptotes either. Okay, now 6, we need to set up a table of signs. And it's not very complicated. Here's x, here's f of x. 0 is the only x-intercept. There's no vertical asymptotes. The function value is 0. Let's just plug in minus 1 and 1. If you plug in 1 to the original f, you get 1 times an exponential. Exponentials are positive, so the function's above the axis there. Whereas at negative 1, we already know it has to be negative. There's not even any need to do anything about this because the function is odd. If you don't believe it, just plug in minus 1. But basically, if f is odd, then whatever it does on the right, it does the opposite on the left. So actually, we know that the function is positive to the right of 0 and negative to the left of 0. It's kind of hard to sketch that. So in order to make things a little more concrete, let's move on to step 7 and look at the horizontal asymptotes if there are any, take the limit as x goes to infinity of x e to the minus 3x squared over 2. And in this particular case, I'd like to write this as x over e to the 3x squared over 2. So what happens as x becomes large? Well, the top goes to infinity, x squared becomes huge, 3x squared over 2 huge, and exponential of it is huge. So you get actually infinity over infinity. The question is which one wins? And we did discuss this a little bit. Again, L'Hopital's rule is the ideal tool, but we haven't done it yet. So instead I will just say, I will appeal to what we looked at when we looked at Chapter 9, exponentials, that exponentials dominate polynomials at infinity. So this exponential kicks butt over the top. This is much, much more powerful than this pure x or power of x. Even if this was x to the million, the bottom would still become humongous in comparison, so that the ratio would be huge over really, really, really huge. That limit is 0. And similarly, the limit as x goes to negative infinity of the same quantity is 0. We don't even have to think about it. We don't even have to think about it. It's an odd function, so the asymptote on the right and the asymptote on the left have to be opposite. If this one was at 5, this one would have to be minus 5. But because this one's at 0, this one's at minus 0, which is 0. So there's a two-sided horizontal asymptote at y equals 0. And now we can draw that in. If we come over to the graph, we know that the function's positive here, so it must come down like this. And similarly, we know that the function is negative here, so it must come up like that. All right, time to do some calculus. Let's pull out some derivatives. For step 8, we have f of x, just to remind you, is x e to the minus 3x squared over 2. So let us differentiate by using the product rule and the chain rule. The derivative of this is the first term, e to the minus 3x squared over 2, times the derivative of x, plus x times the derivative of e to the something. Well, the derivative of e to the anything is just the same thing, but then you have to multiply by the derivative of this. And the derivative of this is minus 3x, because 2x squared over 2, 2x rather over 2, the 2's cancel out. So you'll get minus 3x. And just to factor this, you get 1 minus 3x squared outside of e to the minus 3x squared over 2. And the interesting thing is, again, where does this equal 0? Well, the exponential is always positive. It can never be 0, as I said before. So it's only true when x squared is 1/3, which means x is plus or minus 1 over root 3. So let us set up a table of signs for the derivative. Well, we know that the derivative is 0 at minus 1 over root 3 and 1 over root 3. And we'll pick 0 in between. 1 is bigger and minus 1 over here. The derivative is 0 at these 2 points, plus or minus 1 over root 3. What happens at 1? If you plug in 1, the exponential is positive. Here you get 1 minus 3. So this is negative. What about at 0? Well, that's positive. This is now positive. How about at minus 1? Actually, you don't even need to plug it in. You can use the fact that f is odd rather, so its derivative is even. So f prime is actually even. Just to remind you, the derivative of an odd function is even. The derivative of an even function is odd. And so this must be negative as well. If you don't believe me, just plug it in. You can see it's an even function as well, because it only involves the even power x squared. But in any case, it must go down, flat, up, flat, down. And that's great. This is a minimum. So min x equals minus 1 over root 3, and a maximum at x equals 1 over root 3. Now, step 9, well, let's just do step 9 over here. Step 9 involves getting the y-coordinates of these things. So I'm going to plug 1 over root 3, the maximum, into the original. F of 1 over root 3 is equal to x e to the minus 3, 1 over root 3 squared over 2. And 1 over root 3 squared is a third. 3 times a third is 1. So this is 1 over root 3 e to the minus 1/2. How about f of minus 1 over root 3? Do not bother substituting. Just take this one and whack a minus sign out of it, in front of it. After all, the function is odd. Okay, having found those values, the x-coordinate and the y-coordinate, let me come over to the graph and mark this in. So, 1 over root 3, the height is 1, what is it? 1 over root 3 e to the minus 1/2. So there's a local maximum here. And just purely because the function is odd, there's a local minimum at minus 1 over root 3, comma, minus 1 over root 3 e to the minus 1/2, which is here. So that's a local minimum. Great. We're making big progress. But we still have to deal with the second derivative. So that's steps 8 and 9. Let's do steps 10 and 11. I'm going to use f prime of x is this. Now I have to differentiate that again. So it is the second term, e to the minus 3x squared over 2, times the derivative of this term, which is negative 6x, plus the first term, 1 minus 3x squared, times the derivative of e to the minus 3x squared over 2, which we already actually did. It's just e to the minus 3x squared over 2 times negative 3x. So what have we got when we put everything together? Well, we certainly have a factor of e to the minus 3x squared over 2. We're going to have a minus 6x. We're going to have a minus 3x and a plus 9x cubed. So this is actually minus 9x. You can pull out a factor of x, and you can write this as 9x outside of x squared minus 1 times e to the minus 3x squared over 2. Actually, you could even factor that down to x minus 1, x plus 1. But you can see that this equals 0 when x equals 0, 1, or minus 1. And now this is going to inspire the table of signs for the second derivative. Minus 1, 0, and 1. Okay, so let's pick minus 2, minus 1/2, 1/2, and 2. What the heck? And now I have x, f double prime of x. I know that this is 0 here, here, and here. Minus 1, 0, and 1. And all I care about is the sign at negative 2. Actually, let's just work out the sign at 1/2. I get positive, negative. Exponential is always positive, so it's negative. At 2, I get positive, positive, positive. And now, because f is odd, the derivative is even, the second derivative is back to being odd, and I can just reverse this to be plus and reverse this to be minus. Or if you don't believe it, you can always just substitute. In any case, you'll find that it's concave down, concave up, concave down, concave up. So we have 3 inflection points, minus 1, 0, and 1. So 0, 0, we've already seen. This is an inflection point. How about 1? When x equals 1, f of 1 is 1 e to the minus 3/2, otherwise known as just e to the minus 3/2. And x equals minus 1, we get f of negative 1 is just the negative of this, minus e to the minus 3/2. So there are our 3 inflection points. Let's just mark them on the graph. we have one at 1, comma, this point here being e to the minus 3/2. So the curve must go through here, and it's concave down, and then it switches to concave up. So the tangent kind of goes through that point. Then it's concave down, but it switches to concave out at the origin. So we have another inflection point. None of these inflection points are horizontal, but I put the tangent through there to show. And then, of course, the thing is an odd function, so we must have at minus 1, comma, minus e to the minus 3/2 another horizontal inflection point. And that's exactly what the graph looks like. So you see how we put all the pieces together. By the way, if you wanted to make any of your tables stop at 0 instead and say, you know what, I'm not going to do the left part in any of my analysis, just graph the right part and then reflect it because it's odd, that would be fine too. All right. So I have a little more time, as I had hoped, and I have one more example, which is probably the trickiest one. So I'm just going to do that, and then we'll be done. But first, I have to grab my notes and see what the example actually is. The grand finale, example 4. The aim is to sketch y equals f of x, which is x cubed minus 6x squared plus 13x minus 8 all over x. All right, let's go through it. 1, put minus f, put f of minus x rather. You get minus x cubed minus 6 minus x all squared plus 13 minus x minus 8 all over minus x. I don't have high hopes for this. Get minus x cubed minus 6x squared minus 13x minus 8 divided by minus x. I mean, even if you take that minus and put it up there, everything's going to be a positive, and that's going to screw you up. That's not the same as this. So it's neither. I'm afraid no symmetry this time. Okay, how about y-intercept? Put x equals 0. And unfortunately, because of the 0 in the denominator, y does not exist, so no y-intercept. X-intercept, we need to solve x, the denominator doesn't matter, so we need to solve x cubed minus 6x squared minus 13x, plus 13x minus 8 equals 0. That's a pain. It's a cubic, and we don't have a cubic formula. There is one, but it's really messy, and you're not expected to know it. Actually, the guy who invented it, or the guy who claimed he invented it, didn't want to tell anyone what it was. He thought he could charge people to solve cubics for them and keep it a mystery, but it didn't last that long. Maybe there's something in that for all of us. Anyway, question is, without a cubic formula, can you just guess a root? Here's a nice little fact. If all the coefficients are integers, and it's monic with a 1 out the front, actually the only possible solutions are factors of the constant term, in this case, negative 8. So it could be 1, 2, 4, 8, minus 1, minus 2, minus 4, or minus 8. Those are the only possible factors, actually, which are rational. There could be irrational factors as well. But if you want to have a nice factor, it's got to be one of those numbers. So let's just try 1. If I plug in 1, I get 1, minus 6 is negative 5, plus 13 is 8, minus 8. Yes, it's 0. X equals 1 is a factor. Or x equals 1 is a root. This means that x minus 1 is a factor. So unfortunately, we're going to have to do a long division to find out what the other factors are. So let's put x minus 1 into x cubed minus 6x squared plus 13x minus 8 and do a long division. X into x cubed is x squared. So you get x cubed minus x squared when you multiply through. And you're left with this minus this is negative 5x squared. Carry the 13x, and you'll get a minus 5. So I have minus 5x rather. That times this is minus 5x squared plus 5x. Then I'm going to have 8x minus 8, and of course that's just 8 times this factor, and we're done. So the other factor is x squared minus 5x plus 8. Maybe, though, that's a quadratic. Maybe we can factor that further. What's the discriminant, though? B squared is 25 minus 4 times 8 is 32. The discriminant's negative 7. Discriminant, which is normally written as delta, is negative, so this does not factor over reals. No solutions to the quadratic equation, x squared minus 5x plus 8 equals 0. So actually, x equals 1 is the only root. This is the only x-intercept. If the quadratic had a positive discriminant, you would have 2 other x-intercepts. Or maybe one of them would still be x equals 1, actually. That would be possible. So you might only get one more, but or even they might both be x equals 1. But in any case, that doesn't occur. The discriminant is negative, so there's no other solutions. We found the x-intercept. Okay. Step 4, we need to consider the domain. And if you look at the original function, the only problem is the denominator could be 0, and that only happens when x equals 0. Now, the numerator is not 0 then, so we're going to get a vertical asymptote at this point. Denominator is 0, the numerator is not 0, we'll get a vertical asymptote. So let's draw up a table of signs for the function. X, f of x. What do we know? We know x equals 0 is bad, because f is not defined there. And we know f is 1 is the only x-intercept. So let's test minus 1 and a half and 2. We're going to plug that into the original function. Okay, actually, the simplest way to do it is to rewrite the original function. I'll just do this here. We can rewrite it as x minus 1, x squared minus 5x plus 8 over x. Now, when I plug in negative 1, that factor is negative. Actually, this factor is always positive. Because its discriminant is negative, this means that x squared minus 5x plus 8, if you were to graph that, it always lies above the axis. Could always lie below, but it can't because of the 8. It has to go through 8 and never touch. So actually, at minus 1, this is always positive. That's negative over negative, so this is going to be positive. At a half, it's negative over positive. It's negative, whereas at 2, it's positive over positive. Positive. Now, it's about time I started collecting some of this information. So I'm going to delete this old graph here and start drawing the new one. What do we know so far? We know there's no y-intercept, no symmetry. But we do know that there is an asymptote, vertical asymptote along the y-axis, and that at x equals 1, you have an x-intercept. We know that to the left of this we have a positive value. To the right we have a negative value. It goes through 1, and that's all we know. So let's continue our work. We still have 10 minutes to finish, about that. So for step 7, I would like to spend a little bit of time on this step. What is the limit as x goes to infinity of the original function, x cubed minus 6x squared plus 13x minus 8 over x? Well, in order to do this, I don't even need to multiply and divide. I actually am going to cancel out a factor of x. So I'm going to get x squared minus 6x plus 13 minus 8 over x. And ask yourself what happens as x becomes large. Well, clearly this term goes to 0, and the x squared term dominates. So actually, this just becomes infinity. But it's not just infinity. In fact, it looks like this behaves like the highest degree term. And you'll see that the same is true for negative infinity. If you just change this to negative infinity, that goes to 0. Once again, though, the dominant term is the large one. So what does that mean? It means that y equals x squared, the normal parabola, is a sort of, I don't know, it's not like a horizontal or even a diagonal asymptote. It's a sort of curvy asymptote. So actually, if I come over to the curve here and attempt to draw y equals x squared, it's a parabola. It doesn't really matter what's going on down here, but I'm going to claim that the curve, as you get larger and larger, gets quite close in some sense to this function here. I don't know whether it's above or below. So it's not really an asymptote at all. But if you were to zoom out on this function, whatever wobbles and asymptotes it has here, if you just look at it, then you will see that it looks like y equals x squared, except for some weird stuff in near the origin. But the overall big picture is x squared, because when x is really huge, positive or negative, these three terms don't count. So of course, the same would be true for a diagonal asymptote. If instead of x squared it worked out to be, say, 3x, then y equals 3x would be a diagonal asymptote. That's what the function would look like if you zoomed out a long, long way. Okay, we have a few more steps to worry about, which I will just cover over here, and then we can complete the picture. We need to take some derivatives. Now, rather than use the quotient rule on the original function, I am going to use the form that we've just seen in the limit when we divided by x. That's the easiest way to differentiate. So let's write f of x in that same way as x squared minus, what was it, 6x plus 13 minus 8 over x. And we need to, for step 8, look at the derivative. You get 2x minus 6 plus 8 over x squared. Remember, the derivative of 1 over x is negative 1 over x squared. And so now, I guess what I'll do is I'll pull out the 1 over x squared and write this as 2x cubed minus 6x squared plus 8. And this is a little bit unfortunate because, well, why is this unfortunate? It's unfortunate because we have another cubic to solve. So, in order to solve this, let's try to guess a root again. Let's try x equals 1. You get 2 minus 6 is negative 4 plus 8. That's no good. That's 4. How about x equals negative 1? Well, then you get negative 2 minus 6 is minus 8 plus 8. Aha! X equals minus 1 is a solution of this equals 0. So maybe I'll just be consistent with the way I've written it up before and write equals 0 when x equals minus 1. But is there any other solution? Well, I'm afraid we just have to do a long division. I'll have to do that over here. I'm sort of running out of time, but I really want to finish this example. We know, I'm going to take out a factor of 2, actually. So we know x minus 1, we want that as a factor of x cubed minus 3x squared plus 0x plus 4. Notice when I divide, I fill in the 0x, and I've also pulled out a factor of 2 to make it a little bit simpler. And I know x plus 1 is a factor, not x minus 1, Remember, x equals minus 1 is a solution, so x plus 1 will be a factor. So anyway, just whipping through this long division. Let you check out those details. And I get x squared minus 4x plus 4. And so actually this one does factor into x minus 2 all squared. So, right. So this actually, I could have factored as 2 over x squared outside of x plus 1, x minus 2 all squared, and we see that x equals 2 is another solution. So we have critical points. Let's draw up a table of signs. We have critical points at -1 and 2. But, my erasers are collecting. Unfortunately, we also have a vertical asymptote at 0. So we're going to need all these points here. The derivative is 0 here, and is undefined at the origin. And so let's just fill in some points. And we need to plug this into this factoring here. Luckily, that's always positive. That's always positive. So it's only the x plus 1 that makes a difference. That's negative here. It's positive, positive, positive. So the function decreases there. It has a minimum at -1. Then it increases. That's how I know it's a minimum. There's an asymptote, and then it's up, flat, up. So this must be a horizontal point of inflection. So just to summarize, x equals -1. That's a minimum. And the height of the function, we need to put it back into the original f of -1. And if we do this, we get 1 plus 7 is 8, plus 13 is 21, and you're going to get 29. So we know that there's a local, where did I draw this graph? It's over here. Actually, according to my notes, it's 28. Where did I go wrong? Put -1 in, you get 1, minus 6, plus 6 is 7, 28. Yes, I don't know how I got 29. It is 28. So let's just come over here. Sorry about all this on the video. Must be getting a little bit dizzy by now. We know we have a local minimum at -1, 28. So if I plug that in here, that's going to look like this. On the other hand, running back over, x equals 2 is a horizontal point of inflection. And f of 2, well, you plug it in, you get 4 minus 12 is -8, plus 13 is 5, minus 4. It's just 1. So if we come over here and put in the x-coordinate, the y-coordinate of 1, we see we have a horizontal point of inflection here. Now that's a bit of a problem because it's supposed to be asymptotic to this graph. So unfortunately, I am going to have to climb on a step stool and draw it all the way up to that corner if I want to do it in perspective. What the hey, I'll just expand it out here and you'll have to use your imagination. There's a much better sketch in the book. But notice how I have a horizontal point of inflection there, and it's important to label that. So we're sort of developing the shape of this thing. Unfortunately, we have one more step to do before we're done, and that is to look at the second derivative. To do the second derivative, I'm going to take this expression for the first derivative and differentiate it. And I will simply get 2. Think of this as x to the -2. So it's minus 16x to the -3. The derivative of the constant, of course, is 0. So if you factor this, you can write it as 2 over x cubed outside of x cubed minus 8. Now that is a very simple thing to solve. The only solution to x cubed equals 8 is 2. So this is equal to 0 when x equals 2 only. And so we can draw up a table of signs for the second derivative, being careful to include the fact that the second derivative blows up at 0. So you have to include this. You have an asymptote there. Let's pick -1, 1, and 3. Plug in -1. That's negative. That's negative. So the second derivative here is positive, concave up. At 1, that's positive. That's negative. So it's down, concave down. What about at 3? Then everything's positive. So it's concave up. So this is a point of inflection. Thank goodness it's a point of inflection, because we already know that x equals 2 is a horizontal point of inflection. The main thing we've learned is that there's no other point of inflection. And we already know that f of 2 is 1, so we don't even have to find the y-coordinate. Instead, we have to come back over here and finish this graph. I'm going to join this and this. We've got the local minimum there. We don't have any other wobbles because there's no changes in concavity. Down here, I'm going to join this around through 1. It's not flat at 1. The derivative doesn't vanish there. It does vanish at 2, so it is flat there. We have a horizontal point of inflection at 2, and then it comes up and it's sort of asymptotic to y equals x squared. And there's no other points of inflection than there. And just to finish off, a little word about why we've been doing all these sketches instead of using a graphing calculator. If you use a graphing calculator to draw that graph, you're probably either going to get a zoomed out picture that just looks like this, it just looks like y equals x squared, and you won't be able to see what's going on there, or you'll get a really zoomed in picture that won't show you this behavior. So you kind of have to really play with the graphing calculator to get a big picture. But notice how, doing this work, we've really understood the key parts of the function, the asymptote, the horizontal point of inflection, the intercepts. We know a lot more about the function. Anyway, I'm all out of time, so see you next time.